Turkey's gone, but someone's
Okay,
still
so let's go back and just
Diane has a craving
look
for
at the
savings,
syllabus
so
here.
she's
Thanks
heading to
for
Best Buy's Black Friday
bringing
event
that
for
up.
this season's biggest doorbusters, like a Dell laptop for $299.99, or this Samsung 60-inch 4K
Kicked
TV for
myself out of my own
$799.99,
shell
or
there.
she can save online all week long. Diane came hungry, but she's leaving victorious. Win the holidays at Best Buy. Doors open at 5 p.m. on Thursday and 8 a.m. on Friday. Always open online. Diane's still hungry this Black Friday, so she's chewing up savings on a Dell laptop, a 60-inch Samsung 4K TV,
Yes,
and more.
let's take a look at
Diane's
the
stuffed, and so is her
end game
Win
for
the
due dates
holidays at
here.
Best Buy.
I know, snuck right up, didn't it?
The Tucson is completely
Okay,
redesigned
so
for
this-
2016 with a reworked interior and
For better or worse, this list of due dates actually
1.6-liter turbo
matches
7-speed dual
this
clutch
semester
transmission.
pretty well. So
The Tucson is
I'm calling this lecture 12.5. So more or less, this is week 13. So technically, problem set 3 should be turned in. So exam 4 was already launched. It would be great to have problem set 3 done by this time next week. And then if you could finish, and then exam 5 is title and geothermal. So I'll launch that at the end of next week. Summary 5 is due at the end of finals. Well, let's see, no. Summary 5 is due at the last full week of class. So here's Thanksgiving, where we are now, so that can be turned in this week. Here's the second to last week of class, which is next week. Here is the last week of class, and just get exam 6 finished up during finals week. Like I said, the finals bonus, it's just a bunch of kind of fun problems. You know, like I said, don't study for it. Takes a couple hours. Take it. It's fun, and they're the kind of problems, honestly, that I think will serve you well in later life because they kind of get you thinking in an engineering way. Like for example, the one we talked about the other day is if you're going to burn however many tons, 40, 30 billion tons, 20 billion tons. No, 9 billion tons. I think it's 9 billion tons of coal we're sort of slated to burn this year. If you're going to burn 9 billion tons of coal and it's all on one train, how fast is that train going? Yeah, because you got solid coal coming in one side and CO2 coming out the other. So that's the problem. How fast is that train car going into the CO2 machine? It's going to be what, 5 miles an hour, 700,000 miles an hour? I don't know. It's going to be some number because I think so. That's the kind of problem that I'm going to throw at you on the phone. Just get you thinking and
this Black Friday, Diane has a craving for savings, so she's heading to Best Buy's Black Friday event. For the
so let's go back to
for $299.99, or this
Chapter
Samsung
9.
60-inch 4K TV for
Geothermal.
$799.99.
So is that clear? Answer your questions on the last
Diane
couple weeks?
came hungry,
Okay.
but she's leaving victorious. Win
So
the
there's never
holidays
two
at
things
Best
due in a
Buy.
week,
Doors
unless
open
you
at
want
5
to count
p.m.
the final
Thursday
and
and 8 a.m. on
the
Friday.
exam 6.
Always
So like I
open
said,
online.
you're not going to study for the final. You just come in, take it, call it good. If you will, and it's bonus, you don't even have to take it. It's just that much fun. Okay, courses 102. Let's get into chapter 9. This is also going to give me the opportunity to plug my paper. Sorry, but I'm just going to have to do it. this paper of mine
At a glance, the Charge HR is nearly identical to the
is
regular.
just coming out in January. And the reason I mention it in the case of geothermal is because we typically don't think of planet Earth as radiating. I mean, you look at the sun, you're like, okay, obviously the sun is radiating energy at planet Earth. You look at the moon, you're like, well, is the moon radiating? Well, no, it's only reflecting light from the sun. The Earth does the same thing. It reflects, and fundamentally there's only three things that radiation can do. It can go through something, it can bounce off it, or it can be absorbed by it. As it turns out, the Earth does in fact radiate. It radiates at about 60 milliwatts per square meter. So if you remember back to your solar constant, 1,000 watts per square meter, the Earth is at 60 milliwatts per square meter. So it's still, little brown nugget, it's doing something. Yeah, it's visible at some spectrum. But let me just show you this one. Yeah, it comes out in January. I just got the copy, but I want to show you this one little bit that almost did not make it into the paper because the authors, or not the authors, I'm the author. The editors. Well, I don't know. They just didn't see the point. But let me show you the point. And you're welcome to dig into the nitty-gritty on this guy. But what I want to show you is this part right here. You've got two planets, equal size, equal mass, but different temperatures. So the hotter one is going to pump energy towards the cold one. So the hot one is planet A at 289 Kelvin. And so these are actually pretty modest temperatures. These are actually planets versus stars. And planet B is at 283 Kelvin. So, therefore, spontaneous energy transfer occurs from A to B. It's radiant. There's also energy happening from B to A, but the net balance is that it goes from A to B, from hot to cold. That's the way the universe, as we know it, works. So, and this is kind of a different way of discussing. We were talking about watts per square meter. Well, this is just sort of watts per kilogram. And so if we summed up all of those 60 milliwatts that I just mentioned per square meter on planet Earth, and then weighed the planet, we could do the same thing. How many watts per kilogram is that? You can do the same thing for your body. Like if you are running at 100 watts and you weigh 100 kilograms, you're at one watt per kilogram of chemical energy. So anyway, that's what we're looking at. Now, the subtlety here is, and it's not all that relevant for the discussion here, is that the entropy, which is denoted by S, so delta means change, S means entropy, the dot means how quickly it's changing, and then the subscript A just means how quickly the entropy is changing on planet A. And since the planet is pumping heat away from itself, it is becoming less entropic. And the universe is absorbing that entropy or disorder. Now, so the heat transfer rate is Q dot, so Q has units of energy, just happens to be heat. And then there's the temperature of planet A. So 2330 watts per kilogram. We mentioned that the masses were the same. And it's pumping energy at that rate, negative, so away from it. That's how quickly energy is moving away. At this temperature, that gives us an entropy metric. So it means that planet A is losing entropy at a rate of 8.062 watts per kilogram per Kelvin. Planet B is also shedding its own heat and therefore its own entropy out into the universe at a rate of negative 8.233 watts per kilogram per Kelvin. Now, if there were only 2 planets in the universe, and that's all we had to keep track of, we would just add up their changes in entropy. So we've got planet A's, which happens to be negative. We subtract the rate of entropy change from planet B, and we end up with an overall positive. Because the more or less planet B is absorbing entropy from planet A, and then this is sort of what's left over heading out into the universe. So anyway, the whole point of mentioning that is that the same thing happens between the sun and the Earth. It just so happens to be that on Earth, we've got this fantastic set of nanomachines that evolved called photosystem A and B that actually take the junky radiant energy and turn it into usable forms of energy on planet Earth. Okay. So that's all I want to say about radiation, because the Earth does in fact radiate into space because the Earth is warmer than space. Now, how did the Earth get so hot in the first place? Any clue on that? Because it's getting colder all the time. I mean, the mass of the planet is getting colder all the time. But do you know how it got hot in the first place? I don't think it's really gone into that much in the textbook here, but I find it fascinating. Well, the way I understand it, our solar system itself formed through a lot of gravitational collisions. I'm just going to pop back out here. I'm going to see, because I first saw this. So here's Neil deGrasse Tyson, and he's got a fantastic series called Cosmos. And this may or may not be the Earth, it might be the sun, but initially the Earth was really hot because there were a lot of rocks smashing into each other. So you've got gravitational energy creating kinetic energy as these early chunks of matter were slamming into each other. And so the Earth was just a big molten ball of metal, more or less. So it's constantly been getting colder and colder over time. So if you get a chance, check out the first couple episodes of Cosmos, because Neil deGrasse Tyson goes into it. I don't know what that is, some kind of alien. I know. Okay, so and really, we still experience that to a large extent. The tectonic plates that we see here, I mean, you can kind of think of these as just big frozen balls of magma, molten rock, what have you, that just happen to be at the surface. If you've ever made an apple pie, the middle is still liquid, the outside gets crusty and burnt and more solid, so it's just a big round apple pie. The gushy bits in the middle and the more solid parts on the outside. A lot of the heat is still that kinetic energy stored in the form of thermal energy, and there's still a lot of movement of these plates. When they slide past each other, that kinetic energy turns into friction, and you still have heat there as well. So there's a lot more that meets the eye, or a lot more to geothermal energy than meets the eye. Okay. Yeah, so let's take a look at this, and I like these two numbers. So here's chapter 9, geothermal. And it says the amount of heat flowing through Earth's surface, and then we're looking at 10 to the 21 joules per year, is tiny in comparison with the massive 5 times 10 to the 24th. So I'm just right here on page 409. 5.4 times 10 to the 24th joules per year. Yeah. So if we took this number, actually let's take that number, divide it by the surface area of the Earth, and see how many joules per square meter that is. Let's just take a look here. Surface area of the Earth. Well, let's call it 200 million square miles. So let's do 10 to the 21st joules per 200, what did I say, 200 million square miles? Okay. 200 times 10 to the 6th miles squared. Now let's convert that to square meters. So 1 square mile. This will help you for summary 4 too. You can see if you're getting your bang for your buck out of your geothermal plant. 1 square mile is the same as 1,600 squared meters squared. I'm gonna use Excel for that one. Yeah, my poor little calculator is gonna choke if it tries to swallow that many zeros. Okay. So I'm just gonna, well, nah, I'll do it in a couple of steps. Equals 1E21. So that's 10 to the 21st. And this is 200 E6, it's 200 million. And this is 1,600 times 1,600. Throw an equal sign in front of that. Okay, now what we're looking for is equals that number divided by both of these guys. Hang on. Showing off there, I think it's still too much. 10 to 21st joules. 1 square miles. 1 square mile. What did I do wrong there?
Would it be 10 to the 21st, not 1 to the 21st?
Yeah, well, it's no, because if I do it this way, if I do 1 E1, I mean that's 10. So it's 1 times 10 to that number. Right, so that's 1 E1.
Okay.
So there's 1 E21. So it's a 1 followed by 21 zeros. Woo, there it is. square mile per square meter. There are 1,600 meters in a mile. 1,608, but no big deal. 200 times 10 to the sixth. Oh, that's joules per year. Okay. Fine. So that's joule. That's joules. So here's why we need to use our units. That's joules per year per meter squared, right? And now we need watts per square meter. Okay. Now we're looking at seconds per year. So this equals 365 times 24 times 60 times 60. So that's how many seconds there are in a year, I think, right? Equals that divided by that. There we go. Okay. It's the old energy power equation that we learned in week 1. Oh yeah, that one. So I'm just going to turn that into a number. I'll put 3. Yeah, so how I remembered that, I don't know. But I knew that there's 60 milliwatts per square meter. So you could then, and this is the average, right? This is the average planet Earth. Obviously there are hot spots, cold spots, what have you, but that is the average energy flowing off of planet Earth per square meter, 24/7, 365. Whew.
You said 0.68, so you were too off.
I said 60 milliwatts.
Milliwatts, 60.
Oh, yeah. Well, you know what I also didn't do? I didn't put my 8s there. Ooh. And I didn't, 196.9. One, 9, 6, 9. Oh, I fixed it the other direction. Anyway, pretty close. Okay, all right, thanks. All right. Oh, and that's another thing too. I've seen a lot of students turn in problem sets with way too many significant digits. 3 is enough. 3 is plenty. Okay. All right, so this is kind of the big picture. Now, let's take a break, and then I do want to get into this next concept, which is super duper important. And it's called enthalpy. One of those at first confusing words, but then it's very useful once you know what it is. Okay. Yeah, box 9.